Welcome to today's paper reading. Today's paper is titled, Synthesizing Text-to-SQL Data from Weak and Strong LLMs. This paper was published on the AR14 preprint by Jiaxi Yang and colleagues from Shenzhen Institute of Advanced Technology, Chinese Academy of Sciences, and Alibaba Group. The paper addresses the significant capability gap between open-source and closed-source large language models, particularly in text-to-SQL tasks. To tackle this, the authors introduce a synthetic data approach that combines data from more potent models with that from less well-aligned models. This method aims to enhance domain generalization in text-to-SQL models and explores the potential of weak data supervision through preference learning. Additionally, the synthetic data approach is used for instruction tuning on open-source LLMs, resulting in the development of Sense, a specialized text-to-SQL model. The effectiveness of Sense is demonstrated by its state-of-the-art performance on the Spider and Bird benchmarks, effectively reducing the performance gap between open-source models and those derived from closed-source methods. The text-to-SQL task aims to help non-experts interact with databases using natural language, thereby democratizing data access and analysis. Recent studies have shown significant advancements in this area, particularly with powerful closed-source large language models, LLMs, like GPT-4. However, the use of closed-source LLMs raises concerns about openness, privacy, and high costs. In contrast, open-source LLMs have shown comparable capabilities but still exhibit a performance gap when compared to closed-source models. This motivates the evaluation of open-source LLMs in the text-to-SQL task, with a focus on supervised fine-tuning to enhance their capabilities. Figure 1 provides an overview of the Sense framework, which integrates human-annotated data with synthetic data generated by strong models to enhance domain diversity, and weak models for preference learning. This integration is aligned with executors to improve text-to-SQL performance. The figure highlights the importance of diverse data sources and the role of preference learning in refining the model's SQL generation capabilities. The text-to-SQL task involves converting a natural language question into a corresponding SQL query, grounded in a database schema that includes table names, column names, and database values. In more challenging tasks, external knowledge may be required. To achieve consistent results, a standardized prompt structure is essential for fair model comparisons. The prompt includes 4 key elements: the database schema, task instructions, optional external knowledge, and the natural language question. This structure ensures that SQL keywords and schema are presented uniformly, facilitating the input to the language model. Figure 2 presents the unified prompt template designed for text-to-SQL tasks, ensuring a standardized structure for fair model comparisons. The prompt includes 4 key elements: the database schema, task instructions, optional external knowledge, and the natural language question. This structure ensures that SQL keywords and schema details are presented uniformly, facilitating consistent results across different models. The inclusion of external knowledge, when necessary, helps in addressing complex queries that require additional context. This standardized prompt, denoted as X, serves as the input to the LLM, aiming to enhance the accuracy and reliability of text-to-SQL conversions. Table 1 provides statistical information about the strong data used in the supervised fine-tuning stage. It compares the Spider, Bird, and synthetic datasets in terms of average number of tokens and join operations. Notably, the synthetic data shows a higher domain diversity and complexity, indicated by a higher average number of join operations. The methodology is divided into 2 main phases. In the first phase, the base model's text-to-SQL capabilities are enhanced through supervised fine-tuning, SFT. This involves using GPT-4 to generate synthetic data that focuses on domain diversity and complexity. The second phase employs preference learning, where the model learns from incorrect SQL queries generated by weaker language models. This process refines the model's understanding of SQL syntax and resilience to common errors. The model is optimized using direct preference optimization, DPO, which aligns the language model with executor preferences. This methodology was applied using code LLMA models, resulting in the final models Sense 7B and Sense 13B. Figure 3 illustrates the prompt used for synthesizing strong data in text-to-SQL tasks. The prompt includes a placeholder, the underscore level, which is dynamically filled to adjust the difficulty level of the generated data points. To manage token limits, the prompt also incorporates few-shot demonstrations by randomly selecting examples from the Spider training set. This approach emphasizes the importance of domain diversity and the complexity of SQL queries in the generated data, ensuring a robust training dataset for enhancing text-to-SQL capabilities. In this section, we discuss the experiments conducted to evaluate the effectiveness of Synth. We used popular text-to-SQL benchmarks across 5 datasets. The general benchmark Spider includes 7,000 text-SQL pairs in its training set and 1,034 pairs in its development set, across 200 different databases and 138 domains. The challenge benchmark BIRD is a new benchmark of large real-world databases, containing 95 large databases with high-quality text-SQL pairs, totaling 33.4 gigabytes of data across 37 fields. For evaluation metrics, we followed Spider's official evaluation protocol using EX and TS metrics for Spider and its robustness benchmarks. For BIRD, we adopted its official evaluation scripts focusing on EX accuracy evaluation. We compared various baseline methods categorized into prompting methods, fine-tuning models, and open-source LLMs. Sense7B and Sense13B were evaluated, showing significant improvements over base models and other methods. An ablation study was conducted to assess the impact of weak and strong data in fine-tuning. Table 2 presents a performance comparison of various models on the Spider and BIRD benchmarks. The table highlights the relationship between the final models, Sense7B and Sense13B, and their base models, Code-LLM-7B and Code-LLM-13B, respectively. Notably, Sense13B demonstrates superior performance, surpassing the DaleSQL model by 5.98% on the BIRD test set, indicating its effectiveness in text-to-SQL challenges. Table 3 evaluates the robustness of Sense models against various previously proposed methods on Spider-based benchmarks. The Sense7B and Sense13B models demonstrate superior performance, particularly in Spider SYN, Realistic, and SpiderDK. Notably, Sense7B surpasses RESTSQL3B by 1.4% and Sense13B by 5.4% on average. The table also indicates that TS metrics are not reported for DK due to incompatibility issues. Table 4 presents the accuracy of the test suite on the Spider Dev dataset, categorized by SQL hardness levels. The data shows that Sense13B achieves superior performance across all difficulty levels, with notable improvements over the best alternatives in Easy, 1.6%, Medium, 3.4%, Hard, 7.5%, and Extra Hard, 9.7%, categories. This indicates Sense13B's strength in handling complex SQL queries, benefiting from the difficulty control in synthetic data prompts. Figure 4 presents a domain density comparison, organizing domains based on their example count. This visualization reveals a long-tail distribution, emphasizing the extensive diversity within the synthetic dataset. The long-tail nature of the distribution underscores the wide range of domains covered, highlighting the dataset's capability to represent a broad spectrum of scenarios. Figure 5 presents a 2D TSNE visualization that contrasts the last layer hidden representations of original and synthetic data after supervised fine-tuning on the last token. This visualization underscores the role of synthetic samples in bridging gaps left by human annotated data, thereby validating the utility of synthetic data in enhancing model adaptability and performance. Figure 6 presents the development scores for the BIRD and Spider datasets across various supervised fine-tuning data configurations on the Code-LLM-13B model. The scores are reported for both EX, BIRD, and TS Spider, highlighting the performance differences resulting from different fine-tuning strategies. This figure is crucial for understanding the impact of supervised fine-tuning on model performance in specific datasets. Table 6 presents the performance metrics of the Sense model and its corresponding base models across several benchmarks. MMLU for language understanding, ARC Challenge for common sense reasoning, GSM-8K for math reasoning, and Human Eval for code generation. Notably, the Sense13B model shows significant improvement in code generation performance compared to its base model, Code LLM-A13B. Additionally, Sense maintains competitive performance on math reasoning tasks, highlighting its versatility and generalization capabilities across various tasks beyond the SQL domain. Figure 7 illustrates how preference learning significantly boosts the performance of text-to-SQL conversion, particularly in handling critical tokens. This enhancement is crucial for refining SQL queries, ensuring they are more accurate and aligned with the SQL executor. The figure highlights the reduction in errors related to selecting columns, tables, and operators, which are essential for creating complex SQL commands. This improvement is attributed to the use of weak data in preference learning, which helps in minimizing hallucinations and refining the output based on learned errors. In the field of text-to-SQL parsing, early methods such as EarnIt focused on learning representations using attention-based models. Subsequent works introduced fine-tuning-based models, and recent advancements have leveraged large language models, LLMs, like T5. Building on these models, innovative prompting techniques have been explored, such as the automatic generation of chain-of-thought examples and the decomposition of complex tasks into subtasks. Our work differentiates by leveraging open-source LLMs to match the performance of proprietary models and text-to-SQL tasks. In the area of synthetic data, various methods have investigated the use of LLMs to synthesize data. For instance, Self-Instruct introduced a framework for improving instruction-following capabilities, and hybrid rationales were used to develop advanced math models. Our approach stands out by utilizing both large and smaller models for data generation, demonstrating efficacy in text-to-SQL tasks. In this paper, the authors proposed a novel model called Sense, which is designed to explore synthetic data in text-to-SQL parsing. Sense combines synthetic strong data from larger models with weak data from smaller models, enhancing domain generalization and learning from executor feedback through preference learning. Extensive experiments have shown that Sense achieves state-of-the-art performance on well-known benchmarks, significantly narrowing the gap between open-source models and closed-source models. The release of Sense data and models aims to further the progress in the text-to-SQL domain, highlighting the potential of open-source LLM to be fine-tuned with synthetic data. However, the method has limitations. Due to limited computational resources and time constraints, the authors were unable to fine-tune their method on larger language models, such as Llama 2-70B. The effectiveness of synthesizing data on larger models remains unclear. Additionally, the evaluation mainly focused on the text-to-SQL task and the potential of the data synthesis technique across diverse tasks, including code generation and math problems, remains to be fully examined. Thank you for watching.